normal modes for a given molecule. So benzene will have 12 into 3, 36 minus 6, 30 modes. Benzene will have 30 modes. Naphthalene will have a lot more. A protein molecule will have enormous number because the number of atoms in that system will be huge. So you therefore see that as the molecular size increases, the number of fundamental down steps, if you may call it that way, actually increases. The molecule actually does a very complicated motion, but all of which can be resolved into a bunch of these very fundamental modes, which is what we call as a normal modes. You can actually calculate it from classical mechanics. You can simply use a bunch of oscillators with a spring, and you can see what the normal mode would be, and that can be done. What we have essentially done for the molecule is exactly that. We have actually tried to calculate what the normal modes for the molecules are. For carbon dioxide, this is one normal mode. This is the other normal mode. And this is these two are the other two. So there's 4 modes: symmetric stretch, anti-symmetric stretch, and 2 bends. And we've already seen the symmetric stretch is going to be, you can't see that in this thread because it's d mu over dx is 0. But the anti-symmetric stretch, yes. Bend, yes. But is the molecule doing all 4 at the same time? Yes. Because even at absolute 0, the molecule sits in V equal to 0 level, which is a vibrating level. It's not a quiet level. So even at V equal to, even at absolute 0, the molecule is doing this, plus this, plus this, plus this. If you excite one of them, then of course one has a larger amplitude, other 3 continue to be the same. And therefore the net motion that the molecule will show for you is going to be different. But I still know what it is doing. It's just doing one quanta extra in that one mode, and the others are still what they used to be. So let's see whether we can and you can see this calculation actually gives me all the vibrations. 6 vibrations, 1, 2, 3, 4, 5, 6. They are all being named, numbered as 1, 2, 3, 4, 5, 6. It also gives me the frequency of each of these vibrations. So if you do an experiment, you know where to look for them. And the last column is relative intensity, meaning that if you took the 2027 vibration as unit intensity, the strongest of them all, then everything else is related to that in those units. And the first vibration you can see is actually 0 intensity. So it's not going to be very active, and it's 0 intensity because for that vibration, the change in dipole moment will have these 0. Let's take this one here. So what is it doing actually? It's got this carbon, it's got the 2 hydrogens, it's got the oxygen. But this particular mode, what is it actually doing? It's just doing the hydrogens this way, and it's almost mimicking what you saw for water. And it is almost like the antisymmetric stretch in the case of water. The oxygen is doing nothing in this part. So we say this is a normal mode that is centered around an OH stretch. The OH stretches are going back and forth. And which way are they going? Symmetric or an anti-symmetric? Anti-symmetric. Therefore, it's an anti-symmetric stretch of the 2 CH groups. very much like what you saw in the case of water. Little while later we will see. You have to be able to correlate these in terms of things that you already know. The moment you look at this, you must say, nothing new, I already knew it. It's the case of water. So let's see the next one. And another pretty large intensity is 0.9. It's a relative intensity point of view. It's 0.9, meaning it's almost as strong as the strongest one in that particular series of vibrations. Again, you know this, you have seen this before, and this is basically the normal mode that looks like the symmetric stretch for water. The earlier one was the anti-symmetric stretch, this was the symmetric stretch, and look at the frequency, it is 3160, and the earlier one was higher. And it generally turns out that the anti-symmetric stretches will be higher in frequency than the symmetric stretches. The force constant actually make that happen that way. So this is the symmetric stretch, and still the oxygen is doing nothing. So while there is one part of the molecule that's going berserk, doing all these vibrations, oxygen is just sitting there idle. It simply means that this vibration or this motion at 3160, don't take these numbers too seriously, because you'll always find that theory has correction factors that you have to throw in to make them agree with your experiment and so on. But at least it tells me it's somewhere around the 3000 region. Now this is something that you need to imbibe at some point in time. Namely, where are these frequencies coming for these different groups? If I say it's an OH stretch, you should immediately be able to recall that yes, it comes somewhere in 3000, 3200 wave numbers. That's something you need to know. But of course, you'll always allow that one sheet of paper, so you can always put these numbers and bring it over and use that for your exam. I don't have a problem with that. Because in real life, if you have forgotten the frequency, all you do is go look up a handbook and see where these occur. But at least you must know where they show up roughly. You must be able to say that the OH stretches occur somewhere near 3000, 3200 wave numbers. And that's important for you to recognize. So if you actually record, I'm very sure many of you have recorded the infrared spectra, and I'm very sure you always got some hump near 3200, 3400. And what does that hump do? Moisture. And try as you may, you're not going to get rid of moisture. It's the nuisance in your spectrum. It will always show up. Unless you pay very close attention and somehow take extra care to remove it, you'll always find that moisture will be an inherent part of your experiment. Let's look at something else. This has relative intensity 1, mind you, probably the strongest feature for this molecule. Let's see what that is. Where's the main action? In the CO, of course, while the CO is doing this, the H also has to move. But the main activity is actually the CO stretch. And therefore, this is actually the carbonyl stretch for this molecule. And every molecule that has a carbonyl group, you will find that it will show up at this frequency. In actual experiment, the carbonyl group shows up somewhere around 1700 wave numbers. 1700 to 1750 wave numbers is where the carbonyl group will show. So if you ever see in your infrared spectrum a very strong feature somewhere near 1700, then you know what you're looking at. You're looking at an aldehyde or a ketone or an ester of some sort, because that's where the carbonyl features are supposed to show up. And that's basically what it is, where the CO stretch is actually, the oxygen was quiet so far. In the last two vibrations that I showed you, oxygen was really quiet. But all of a sudden we now find that the oxygen is really added, and therefore this is basically what we call the CO stretch.
So the frequency you mentioned there is the frequency of this complete
Moment I say it's, I was going to tell that again. Moment I say it's a normal mode, this fellow vibrates at a certain frequency. All periodic motions will have the same frequency in there. All of them will have the same period. All periodic motions. There is a certain periodic motion associated with hydrogen, a certain periodic motion associated with oxygen. All of them will move at the same frequency and the same phase.
But then what do I say? C double bond O stretching?
Yeah, this is a carbon C double bond O stretching. Because it's a small molecule, you see that both the CH is contributing, but then if you look at the kinetic energy, how much has been disposed, the heavier atoms actually carry a larger energy in their whole process. And therefore you say it is actually if you look at bigger ketones and bigger aldehydes and so on, you actually see only this guy making much of a excursion, with others making very little of it. but this is a problem stretch, and that's basically what it is. What is that looking like? That's like the water bend, and very similar to that. So you therefore see, and again, the oxygen is doing hardly anything in this case. It's basically the CH bend that's doing this. Let's go to these are things you don't have in the case of water. Why did you not have it in the case of water? In the case of water, this would have actually meant a rotational motion. It's because of the oxygen out there that this is sort of rocking. If the oxygen was not there, this water molecule would have done this. And therefore, you can see, putting the extra atoms in there has given rise to new normal modes. We know that it's 3n minus 6 extra. And that's the reason why this would be. If you turn this around, you'll see what's happening. This is again an out of plane, this is what we call as the out of plane bending. Because the formaldehyde molecule is planar. And what is this motion really doing? It's getting the molecule sort of fanning it out and getting it out of plane. And therefore this would be an out of plane bending for the water molecule. So I won't bother you now with this, but then you have already learned the different irreducible representations for the C2V molecule. Right? This is a C2V molecule. And what are the irreducible representations for C2V? A1, A2, B1, B2. And you will see that all these vibrations that you have just seen, the 6 vibrations that you have seen, will actually belong to one of these 4. They will belong to one of these 4. They will either be a representation for A1 or A2 or B1 and B2. We won't get into how this can be done so on and so forth, but I'm just trying to recall what we studied last time, that every point group has these irreducible representations. And we said it Z transforms like A1 for the C2V. We said X transforms like B1 and Y transforms like B2. What do we mean by that? That the Z coordinate actually has the symmetry of the A1 representation. You will see over here that the symmetric stretch has the representation A1. The bend has the representation of A1. And what do I mean by that? If I take the symmetric stretch, for example, that's what the symmetric stretch is. Just putting an arrow to tell me it's going in the same direction. What are the symmetry operations for the point group C2V? Right? And if I had 1, 1, 1, 1, what is that? That's A1. And what would I have here? Is the Z. Z was the basis for representation for the C2V. We saw that in the last. We did see it, right? Okay. So that was what it was. Now let's take this vibration. When the molecule is doing this. If I do an E on this, what do I get? The same thing. And therefore, what would I put here? 1. If I do a C2 on this, what would I get? This arrow goes here, this arrow goes here, it's still symmetric, and therefore I would still get 1. If I did a sigma Vxz, which is the board plane, what do I get? 1. Nothing happens. If I did a sigma Vyz, which is the plane going right here, these two interchange, I still get 1. Therefore, if I had used this as a basis of representation, this normal mode as a basis for representation, what irreducible representation am I coming down to? A1. And therefore I say that this vibration has A1 symmetry. You can take every one of those vibrations I showed you and play this game, and you will find that every one of those vibrations will actually have A1 or A2 or B1 or B2. It will fall into one of these categories. And of course, once you know that, there's a lot more powerful information that you can derive once you know the symmetry of the vibration. But the point I'm trying to make is the following, that once you know the normal mode, the way the molecule vibrates, I should be able to go back to the point group of that molecule and say what this vibration really belongs to which irreducible representation it really belongs to. And that's basically, and once I know that, I can derive selection rules and so on and so forth. We won't push this any further, but this is just to give you an idea of what could happen. When I say we won't push this further, I'm not going to push this further at this point in time. But when I do get to Raman, we'll push this argument a little harder and see how we can get more information for us. But just to give you something more, let's talk this molecule. Benzene must have 30 vibrations. I have all 30 of them, all the frequencies, all the relative intensities, and we can look at it. But let's look at some of them. This is not really of any intensity. You really won't see that in an experiment. But let's see what the vibration looks like. Usually what you can do is get one of your favorite film songs or whatever and put it on the background. It will match. It will work out quite well actually. And it doesn't matter what song it is. Which leads me to believe that to dance in these movies, it doesn't matter when you know dancing or not. Whatever you do will fit. Just like whatever the molecule does fits. So you can do anything. You can get your latest or your oldest Hindi songs or film songs or whatever, and they will match up with. This is actually, what do you think this motion is? It's a very symmetric motion. Benzene has zero dipole. Do you think there is going to be any change in dipole when this is happening? There is no change in dipole. And that's the reason why this has zero intensity. So you see why that is happening. This is one of the common modes of benzene. Zero intensity in infrared. You will not see it in infrared. The molecule is still vibrating at 3388.9 as given by this calculation. I don't know whether that's true experimentally, we will see. But at 3388, but what is the stretch really? It's a symmetric CH stretch. The H's are going back and forth. The symmetric CH stretch, all hydrogens moving in the same direction as the other, relative to the center. No change in dipole. The molecule basically is not going to absorb light at this particular frequency corresponding to this vibration mode. I'll show you another one. What's the difference between this one and the last one? The whole ring is going up. The last one, the CH is went out. That was basically extension of the CC. But this, the whole ring, and what does it look like? It almost looks like the benzene is breathing. Okay. And that's what it's doing. And in fact, this is even called the breathing mode of benzene. In fact, we like to refer to modes which are very similar or which can be related to something very, very physical. So this is of course the breathing mode of benzene. You have the wagging mode in some molecules because it looks like the wagging of a dog's tail. You have a rocking mode where the molecule basically does this. You have a bending mode, rocking mode, wagging mode. This is the breathing mode. So you see that it has been related to something quite physical so that you remember what it is. Again, a breathing mode is going to have zero change in dipole. And therefore, this mode will not be seen in an infrared spectrum. The reason I am harping on this is for a very specific reason. Because when we go around, we will come back to these modes. So the question you're going to ask me is this: if this mode doesn't absorb in the IR and doesn't make a transition, how do we even know this is happening in the molecule? Just because you calculate it? No. We should be able to see this in an experiment. But the infrared experiment does not allow me to see it because there is no change in dipole. dmu over dx is 0. Therefore, I am not going to see it in the infrared. But I must be able to see it somewhere. And we will see when we get to Raman that these modes can actually be seen in certain other experiments. And that's the reason why we know that these modes actually perform these wonderful down sequences that the molecules do. So we can go on and look at all the other modes. Now these CHs are all going in haywire motion. Now there is some method in the madness, it's not completely haywire. And you will see that this mode actually leads to a change in dipole, and therefore this molecule in this vibration mode can actually be absorbing light to make a transition from 0 to 1, and you will see. But again, where is this occurring? It's occurring somewhere near 3300 wave numbers. And any CH stretch will show up in the green. We already said that the OH shows up near somewhere near 3200. If OH shows up somewhere near 3200, the CHs must also be close by. Why? Well, what's the frequency given by? 1 over 2 pi root of K by mu. What's the big difference in reduced mass between OH and CH? Not a whole lot. H is still there, and that determines the reduced mass. The carbon and oxygen just add on very little to it. So the reduced mass is actually determined by the hydrogen. So the reduced mass is about the same. The force constants are not very different, and therefore you will find OH, CH, SH, NH, all these hydrogen-containing groups will all show up in their frequencies somewhere between 3000 and 3500. So the way you remember one, and then you use logic. If I know carbon OH, and you have to remember OH, because every time you record an infrared spectrum, it's going to be a nuisance. It's going to show up at 3200, 3300, 3400 in your, as a big peak, because it's an impurity that you will always be seeing. So you will know what are the blobs at this 32, 3300. Once you know that the OH stretch comes around that, you must be able to say that the CH stretch, the SH stretch, the NH stretch, all of them will show up somewhere in that region. If I tell you the carbonyl, which you saw a little while ago, shows up somewhere near 1700, where do you think the C double bond C should show up? Well, somewhere near there. So if I know carbonyl comes around 1700, you must expect to see the C double bond C, the C double bond S, all of these to show up in that region. So you sort of have to have your own ways of remembering this. If you know some, you can always guess where the others are going to show up. And this is very, very important because in real life, when you record an infrared spectrum and you look at it, you can't be reaching out for a handbook every time to see where it's going to show up. You've got to use some logic. Well, I know that the C double bond O shows up at 1700. I see a feature around this. I know my molecule doesn't have a carbonyl. I know it has sulfur, so it's quite likely I'm seeing a thiocarbon, C double bond S, and I know that the group is present in this molecule. So you've got to be able to make such decisions by simply knowing a few functional groups and then being able to deduce where the others would show up. Now, the nice thing about the infrared spectrum is that if I have a carbonyl in formaldehyde, I have a carbonyl in acetone, I have a carbonyl in an ester, I have a carbonyl, let's say, in some other molecule, it doesn't matter. As long as the carbonyl is present, it will always show up somewhere near 1700, because that's the normal mode corresponding to this. So, irrespective of what the molecule is, if I see a 1700, I know a carbonyl is there. In other words, what I am doing by this method is doing a functional group analysis. So, infrared spectra is extremely powerful in giving me functional group information. OH, I know where it comes. Carbonyl, I know where it comes. C double bond C, I know where it comes. P double bond O, 1300 or thereabouts, I know where it comes. C single bond O, 1000 wave numbers. I know where it comes. So if I look at these frequencies, I know what functional groups are present in this molecule, and therefore, if I'm an organic chemist, taking a double bond, hydrogenating it, and producing a C single bond C, and I want to know if the reaction is gone to completion or not, what do I do? Simply record an IR spectrum. If I see the C double bond C, which would come somewhere near about 1500, 1400 wave numbers to begin with, and in my product it's not there, I know my hydrogenation has gone to completion. But if in my product it is all still there, then I know my reaction hasn't gone. So it's very powerful in figuring out whether you have been able to push a reaction like that. Take a carbonyl and you want to reduce it to an alcohol. Take an infrared spectrum before and after. If the carbonyl group is completely gone, the C double bond O at 1700 wave number is lost, and what you see is just the OH at the end. Then I know I have got the reduction done, and therefore you will see that infrared spectrum, by very simplicity, I mean you have learned how to record one. It doesn't take much to learn how to run that spectrometer, and once you have done that, you are actually in a position to determine whether the functional groups, what functional groups are present in this molecule, and this is what we call as a functional group analysis. Generally, all these important functional groups will show up from about 1000 wave numbers to about 3500 wave numbers. Now this is something that you might just want to remember. 1000 wave numbers to about 3500. So, you have an spectrum, and you will see that 4000 and 400. And you know that a spectrum looks something like that. This is the range, 4000 to 400, is in fact what we call as the mid-infrared region. Mid-IR. Less than this, there's the far IR. On this side, so like a linear IR. And all this near and far, they're all relative to the visible region, because that's where we see light, and we want to relate to everything around the visible. This guy is close to the visible, near IR, far IR. And this is the mid IR. So the experiments that you have been recording in the laboratory are basically mid IR experiments spanning the region 4000 to 400. And somewhere from about 1000 wave numbers or so,